How's everybody doing? Good? Awesome. My name is Blake MacDonald. I'm an undergrad researcher at the University of Colorado, Colorado Springs, and this is my teammate.
Hi, I'm Luke Davis, University of Colorado, Colorado Springs.
And we'll be talking about our research today where we studied how microgravity affects inorganic crystalline structures. Okay. Oh, there we go. Calcium sulfate is a compound with various applications that range from construction to improving water retention in fertilizers. Changing the crystalline structure of calcium sulfate and other similar compounds could, theoretically, impact material function by improving strength and uniformity of the crystalline structures. Our team decided to test this theory by sending samples of calcium chloride and sodium sulfate to the International Space Station and comparing these samples to on-Earth grown samples to determine and identify any significant differences between the two samples. We hypothesized that growing crystals in the absence of high gravitational forces improves calcium sulfate by creating structures that are larger and more uniform. Gravity and buoyancy forces significantly impact how crystalline structures form on Earth. These strong forces can cause irregularities, whereas in space, we can expect more controlled environments and promote more uniformity. If proven to be true, fertilizers or other materials could have more uniform crystals, having more applications in the field of interplanetary colonization, and hopefully making us more affordable to improving conditions here on Earth. Once samples return to Earth, after we do the experiments, and once they have actually, I mean, they did, our team utilized several key resources for analysis to try and improve these structures with change when forming under microgravity conditions. We employed powdered X-ray diffraction, a machine that shoots X-rays at live structures, to analyze the crystal structures of the samples. We also used red field analysis to characterize even the minute differences between the Earth and microgravity samples, which you can see on the slides. Our team was supported by Dr. McMillan, PhD of Clemson University, and Andrew Pelican, who helped us both with these important experimental analysis. And I'll hand this over to Luke Davis.
Oops. Yeah. So I can talk more about the results that we got. So as you can see, I don't know if I have a laser pointer right here. Nope, that's okay. So ground one and the space one, that's going to be our different samples that we have. As you can see, the intensity spikes are normalized against each other, so they're offset. But what matters is that, that 2 theta, which shows the angle at which the X-rays were diffracted. And those different angles are going to identify what polymorph the crystalline structure is. So as you can see here, they pretty much line up almost identically. So these are going to be pretty much the same crystalline structure. So what we know from that is we can reliably produce these on Earth and in space and get the same structure. The one difference we did really see was going to be the weight fraction results. So as a byproduct, we did create salt in our chemical reaction. However, as we washed that away down here on Earth, we saw more gypsum overall. So it was a more complete reaction when it took place in space, which makes sense as a byproduct of mixing it in space. It mixed better and for longer periods of time, which is a great result. So we can see more complete reaction. We can see better use of those resources in space. So our overall conclusion is that while these structures were not changed in any meaningful way, this is proof that we can manufacture them in space and here on Earth reliably. We can do experiments here on Earth with calcium sulfate for things like fertilizer and know that we're going to get the same kinds of materials on space as we do here on Earth. And while it wasn't larger, it was more uniform. So we did get a better mixing and a better chemical reaction. Gravity and buoyancy forces do play some effects in some roles, but with calcium sulfate, we didn't see any meaningful difference, which helps us better understand how those buoyancy and gravity forces affect overall crystalline structure formation in different roles, so different chemicals. We can better analyze that. And then, of course, the small increase in weight fraction results was showing us that we have better mixing, as I said before. So we just want to thank our partner institutes, and I want to have a special shout out to Dr. McCollum at the University of Colorado, Colorado Springs. She was absolutely instrumental in all of our lab work and helped us understand how to perform these in clean room type environments and to make sure we weren't messing up any of our stuff that we were so awesomely given the opportunity to use and to do. And so thank you very much. Is there a question?
Let me say one thing that's important here. So in a real contest, I forgot to mention this before, your peers ask questions. I mean, it's an opportunity to probe deeper. You know, when you listen to a presentation, you come up with questions that were not addressed in the actual presentation. And so you're invited, and it could be SSEP researchers, it could be a teacher, a faculty member, a parent, but we encourage people to ask questions of the presenters because that's part of the authenticity of, you know, that two-way communication. So we open up to 2 minutes of Q&A.
That's correct. Do we have any questions for this group?
And John has a microphone that he can carry around.
Hi, thank you very much. Can everybody hear me? Yeah. So I'm Roberto Fanganiello from Brazil. A great project. It's very, very nice. I have a question regarding if, for example, there is literature or something already done in simulated microgravity here on Earth that you can compare with your experiments. Thank you.
So in terms of simulation, we don't have any specific simulation of calcium sulfate. There are other simulations. There are other simulations of different materials. We didn't find anything for calcium sulfate specifically. Calcium sulfate only really exists in 2 possible polymorphs, so we weren't sure if that other polymorph would show up or if a new one would show up, and so simulating that would be really difficult, but we did find for lots of different other types of structures simulations, just nothing for our specific. Absolutely. Any questions?
My name is Chelsea Crandall, and I'm from Morgan Community College. I studied geology, so this sort of X-ray diffraction stuff is exactly the kind of thing that I used to study. For your X-ray diffraction normalization and programming, did you find that there was any, I'm trying to remember, did you mention that you did have to normalize it and that there was a shift, or did they line up on their own?
They lined up on their own. They shifted it upwards for that one graph. Okay. I don't know if I can go back to show it or not, but it just, that was just to show how it lined up. The intensity spikes weren't perfect, yes. But the actual theta angle was identical.
And my other brief question, for your gypsum growth simulation on Earth, was that in a similarly controlled environment, or was it like exposed to the air?
Mm-hmm. So we had, I'm not sure how it worked for all the different teams for who's done flight experiments or not. We were given a couple of samples of the NanoRacks fluid mixing enclosure as well as the flight version. Mm-hmm. And so we used the exact same hardware to simulate here on Earth. We created them at the same time. Yep. And then we followed the same procedure that they did on the space station. Tried to do the same time. We were given notification by SSEP when that took place, and we just tried to match that as best we could.
All right, thank you.
Absolutely.
All right, thank you.